Alright everybody, Dr. Pennington here again. I wanted to talk to you today about a particularly important reaction that you haven't seen before. It's called the Diels Alder reaction. In case anybody's wondering, Diels and Alder simply come from the names of the two guys that discovered this reaction. This is known as a 4n plus 2 cyclo addition. It's a really important reaction. Addition, because you're adding two things together to make one. Cyclo, because we're actually going to add these two together and make a ring, hence cyclo means we're making a ring. 4n plus 2, what this means is the number of pi electrons that you're adding together. You're adding 4 pi electrons from here, from these two double bonds, and then these 2 pi electrons from this double bond. Alright, so 4n plus 2 cyclo addition. Basically what happens here is we have the two species here. Now let me just remove those squiggles that I put around here. Alright, there we go. We have the two species here. This is what's known as the diene. Now you've heard the term diene before. It's a compound that contains two double bonds. Ideally in conjugation with each other, or at least that's what you need for this reaction. And then we have what's called the diene-ophile. Alright. So we have the diene, this is the nucleophilic species, and then the dienophile, which is the electrophilic species. In other words, when these two react, this guy takes electrons and attacks here. Usually all that's needed for this reaction is simply heat. Just heat it up a little bit and the reaction will go. Alright. Now a little bit about the diene and the dienophile. Let's talk about the diene first. Because we're going to be making a ring, these two double bonds, this one here and this one here, have to be both pointing in the same direction. They have to be in what's known as an S-cis conformation. In other words, if we just draw this out a different way, for example, if I do put this here, and then I can put my two double bonds like so, you can see here one double bond points down, one double bond points up from the viewpoint of this middle single bond here. These two double bonds pointing in the opposite direction to each other, this is what's known as S-trans. And this is no good for the Diels Alder reaction. We need this S-cis. So we need a single bond here about which this can rotate to obtain this S-cis conformation. It's really important about the diene. Now for the dienophile, the best way for a good dienophile, or to have a good dienophile, is to have one that has electron withdrawing groups on it. If this is the nucleophile, it's taking its electrons and attacking here. So if you can remove electron density from here with some sort of electronegative group or something like that, then that will always work out best. To give you an example, a few good examples of dienophiles will be something like this. This is a good one simply because this carbonyl group can remove by resonance electron density from this lone pair, from this double bond. Something like this would work out just fine. This would be even better because there's two groups that can do the same thing there. A very common dienophile in the Diels Alder reaction is quite similar to that. It's called maleic anhydride. Basically you have a bunch of groups here that can, by resonance, remove electron density from this double bond and make it electrophilic. Anyway, the way the mechanism works, it's really quite simple. One thing to make sure that you do, though, is always keep track of which carbon is where in relation to which other carbon. So I always like to take the 4 carbons of the diene and number them. 1, 2, 3, 4. Don't worry about these other carbons, they're just there, so they're going to be there in the product. And then let's call these two carbons in the dienophile, let's call them A and B. Alright? Now the reason why I do that is because of the way the mechanism works. Like I said, this is a cyclo addition, this is the nucleophile, and what happens is the electrons, the pi electrons in this double bond between carbon 1 and 2 go out and attack carbon B. Hence why it helps for this to be electrophilic. And once that's done, because carbon 1 has now formed a bond with carbon B, it can't have 5 bonds, so this double bond also has to break, takes its electrons and goes down to carbon 4, forming a bond between carbon A and carbon 4. Now you've run into the same problem there. You can't have a Texas carbon here, so this pi bond breaks as well and puts electrons up onto here. We need the extra bond here because this one's broken when this pi bond broke. Anyway, let me show you what's happening here. I'm going to draw out the bonds that we had in our two starting materials. All right. Can you see that the double bond between carbon 1 and 2 has gone? Just as the double bond between carbon 3 and 4 has gone, as the double bond between carbons B and A has also gone. But we have formed a double bond between carbons 2 and 3, so we're going to put that in the product. And I'm going to show the new bonds in a different color just to show that they're actually new, like so. These two are the new bonds between carbons 1 and B and between carbons 4 and A. And that is our product. If I just draw it all out in one color, you can see this is simply it. Notice that the groups coming off each of the diene and the dienophile haven't gone anywhere, they haven't moved or anything, they're just where they were. So the product is always a six-membered ring with at least one double bond in it. That is the Diels Alder reaction. It's a very, very useful reaction. Let me go through a couple of examples. So let's say we had to figure out the product between this diene and this dienophile. Well, what I would always do is make sure the diene is written in a way or drawn in a way to make it easier for you to push your arrows and figure out the structure of the product. So you always want to draw your diene double bond straight up and straight down. It just makes it easier. So I'm going to draw the diene out again. I'm just going to keep it the way it was. Notice there's a methyl group coming off carbon 2 here. We're just going to make sure that's present in the product. And I'm going to take this whole thing and just rotate it down a little bit so that my double bond goes like this. And then I have the rest of the dienophile looking like that. So again, all I'm going to do is push my arrows. That goes here. That goes here. And we form the new double bond here. So notice we have broken 1, 2, 3 pi bonds. We've formed one pi bond and formed two sigma bonds. Got a lot of energy out there because sigma bonds have a lot more energy than pi bonds do. Anyway, we know we're going to make a six-membered ring. We just need a little bit of heat to get it to go. So, six-membered ring. And if you're not entirely sure about what's supposed to go where in your product, well, just label the carbons again. 1, 2, 3, 4. B and A, or whatever you choose to label these. So for carbon A, you can see, well, coming off carbon A, because if we number this 1, 2, 3, 4, B and A, again you can see between 1 and A and 4 and B are the new carbon-carbon bonds. Coming off carbon A, we have our carbonyl group. We know coming off carbon 2, we've got our methyl group. And then between carbon 2 and 3, we have formed our new pi bond. And that's it. That's really it for the Diels Alder reaction. It's really pretty simple. You just got to remember, S for the diene, electron withdrawing groups on the dienophile. So if we have to do the same thing here, we're going to apply exactly the same thinking. All right? Exactly the same logic. Let me just get rid of that box. There we go. I'm just going to number these again. 1, 2, 3, 4. Don't worry about the fact that there's an extra carbon here. And also don't worry about the fact that there's a bunch of other carbons and stuff here. They're still working in exactly the same way. We just need some heat. Now, what we will do now is I'm just going to draw this out again. And I'm going to do exactly what I did before. We form in a six-membered ring. And if we label things the way we did before, just like so, we're going to have a double bond between carbon 2 and 3, if I just push all our arrows again, so that goes to here, this goes to here, and that goes onto there, and then, hang on a minute, and then coming off carbon A and B we have the rest of this, what was maleic anhydride, so we have all this stuff here. So in this case we formed 2 rings, but we already had one present. Now the only thing that you're probably wondering is, well, what about carbon 5 here? Because that kind of just disappeared. Well, no, it hasn't. Notice carbon 5 was connected up to carbons 1 and 4, and it still is. Oops, I didn't draw that one very well. That should go down to carbon 4 here. The thing that I need to alert you to, though, is in this structure it doesn't show a very good representation of where carbon 5 actually is. You can't really have carbon 5 smack down in the middle of carbons 1, A, B, and 4, because there's just no room. So it turns out that carbon 5, being the only sp3 hybridized carbon in this molecule, it kind of sits up above everything else. So I'm going to draw this out a different way that emphasizes the 3-dimensional structure of this molecule. Alright? So stay with me whilst I draw this out. It's going to look a little funky before I finish. Actually, it'll probably look funky after I finish too. But anyway, what I'm drawing out right now is the carbon, the 6-membered ring, 1, 2, 3, 4, B, and A. So I'm drawing out the product that we formed. I'm going to put on our bollocks. Hang on. I'm not going to put on our bollocks. That's not right. Hang on. Let me put the single bond back on here. That goes there. No bollocks anywhere. Well, maybe. And the only thing that I want to show is where exactly carbon 5 is, because like I said, carbon 5 is actually kind of above the plane of everything else. So carbon 5 is actually up here. So this and this are actually the same thing, but you just can't tell where 5 is in 3 dimensions just by looking at this. The point is, both of these mean the same thing, but that's just a more accurate representation. So that's Diels Alder reaction, 3-dimensional view. Now, what if we had to look at a retro style question, retro Diels Alder reaction? How do I go backwards? All right. Well, let's see if we can figure this out. What would I use to get to these products? Well, I'd use a diene and a dienophile. So I know I have my 6-membered ring here. I know my double bond is right here, and notice when we did this all the other times, the double bond always ends up in the same place. It always ends up between where the double bonds originally were in the diene. So that means then when we look at this, I can number this 1, 2, 3, 4. If I want to even just number it 5 and 6, I could do it this way. And that means I know if the double bond in the product has ended up on carbon between carbon 2 and 3, that must mean the diene was originally had the double bonds between carbons 1 and 2 and 3 and 4. Which also means then that the bonds that I formed in making this Diels Alder reaction must have been between 1 and 6 and 4 and 5. Meaning carbons 5 and 6 must have been the dienophile. Here's where we've got to be a little bit careful. Notice the 2 groups coming off the carbons 5 and 6. Notice they are in a cis relationship. Well, that means they must have also been in a cis relationship in the original dienophile. So all that means is we have to show, if both the chlorines are pointing up or down or whatever, we just have to show them both pointing in the same direction. Alright? If we'd had one wedge and one dash, that would have meant they're in opposite directions in the product. Therefore, they must have been in opposite directions in the starter material. Alright? Anyway, that's how we'd make that guy. Now, when we go down to here, again, this is one of these looking things, but it's still exactly the same sort of idea. If I just number the carbons in my 6-membered ring, I'm going to say this is carbon X up here just so we don't forget about it. You can see once again that the double bonds in the diene must have originally been between carbons 1 and 2 and 3 and 4, because in the product the double bond is present between carbon 2 and 3. But also notice what else is coming off carbon 1 and carbon 4. It's that carbon X, which means our diene must have originally looked something like that. And then when we look at the diena file, if we number this 5 and 6 again, notice now there's nothing coming off carbon 6 that we can see, so essentially that means just 2 hydrogens. But coming off carbon 5 is a chlorine and this ketone group. And so all that means we have to do is we just have to represent the fact that those were originally there. It doesn't really matter which way we do it, as long as you recognize, or as long as you indicate that there's a carbonyl group here and there was a chlorine here. Because that shows if they're on the same carbon in the product, they must have been on the same carbon in the starter material. Alright, that's the Diels Alder reaction. Pretty simple. There you go.